We are now in a position to build the full structure of the folded cascode op-amp. So let us quickly do that. The first thing we start off with is the input stage. From the common source NMOS, we will draw the NMOS common source followed by the PMOS common gate folded structure, and the input stage in the single-ended version was a common source NMOS transistor. When you move to a differential amplifier type of structure, the two transistors will be joined together to form a differential pair. As shown here. So this is your NMOS differential pair. The inputs are plus VT by 2 and minus VT by 2, and you have a current source at the bottom, which is some current source, through some transistor M0, let us say, and the input transistors are M1 and M2. Remember that in the single-ended structure, they should go to a node which splits between the common gate PMOS structure, which is folded downwards, and a current source at the top. So if I were to show the current source at the top would be replaced by PMOS transistors. So and at this node you have the splitting of the current between the two paths. So let us say that transistor M1 is connected so, and transistor M2 is connected to this transistor, this PMOS transistor. And finally, at this point, the output goes into the common gate PMOS structure. This is the common gate PMOS structure, and this is the output. Remember, now you need to get a single-ended output, and you need to get a current source at the bottom, and therefore this portion of the circuit will actually have a current mirror. In this particular case, this will be an NMOS current mirror structure. And because we want high swing from this particular structure, we will use the high swing cascode for the NMOS current mirror. And the output is correspondingly taken at this node. So let us now mark the numbers of the other transistors. So M3 and M4 form the common gate structure in the signal path, and M5, M6, M7 and M8 form the current mirror at the bottom, and M9 and M10 form the current source at the top. Now what about the, let us quickly check if the plus and minus signs of the op-amp we have drawn are correct. So if you were to apply a positive VD by 2 to the gate of M1, you expect this current to be positive and this current to be negative in this direction. So this current would be pulled out from this node and through M5 and M7, and this would cause a corresponding current to flow through M6 and M8. And if you look at this path, there will be a current flow from M2 which flows directly into M4, and the sum of these two currents would flow through the output. So clearly the plus and minus signs of the op-amp are as shown. Now let us, now that we have drawn the basic structure of the op-amp, let us quickly do the small signal analysis and try to come up with the expressions for the gain, etc. of the op-amp. So let us start off with the small signal gain of the op-amp. So we want the DC gain of the op-amp. If you were to look at the DC gain, you can see that the current through M1 and M2, because this is a differential pair with this node being a virtual ground, the current through M1 would be Gm times Vd by 2. Flowing downwards, the current through M2 would be Gm times Vd by 2 flowing upwards, because a minus Vd by 2 voltage is applied at its gate. And we are also going to assume that the transistors are designed such that most of this current does not flow through M9 and M10 but flows down into M3 and M4. And therefore, the total current flowing out would be Gm times Gm1 times Vd. Now, where does this current flow? This current flows through the total output impedance at the output node. For the DC gain, we will assume that there is no load, or if there exists any load, it is a capacitive load. And let us quickly calculate the expression for R out. So R out has two components: an upward looking resistance and a downward looking resistance. The upward looking resistance is nothing but Gm4 RDS4 times the RDS of M10 in parallel with the RDS of M2. This is the impedance looking upwards, and that comes in parallel with the impedance looking downwards, which is Gm6 RDS6 times RDS8. So this is the overall output resistance. Clearly then VO by Vd needs to be Gm1 times RO. And as we have pointed out before, this is quite large. This is only a little bit smaller than the the square of the intrinsic gain of a transistor. So this is the small signal gain of the folded cascode op-amp. Now that we have found out the small signal gain, we should also write down the expression for the frequency response of the folded cascode amplifier. So now let us assume, I'm going to show that in red. Let us assume that there are capacitances at every node of the circuit. So you have capacitances from this node, and in fact every node of the circuit. And let us assume that you also have some load capacitance at the output, and so at the output node you have CL plus some parasitic capacitances. As you can see, you now have a large number of capacitances in the circuit, very similar to the telescopic op-amp. What do these capacitances consist of? So for example, let me number these capacitances. See six capacitances, and let us assume that CL consists of the load capacitance plus all other capacitances. For example, capacitance C1 will not be significant for differential mode analysis. This is because the common source node of M1 and M2 is going to be a virtual ground. It's going to be a small signal ground for a differential input. What about capacitance at, let us say, node 4? So let us say C4. So C4, for example, would consist of capacitances, gate source capacitance of M7 plus gate source capacitance of M8 plus the drain bulk capacitance of M5. So you can see there is capacitance from M7, capacitance from M8, capacitance from M5, and of course drain bulk capacitance from M3. This is an example. Each one of these capacitances will have contributions from the respective transistors connected to that particular node. What do we know about the frequency response? The frequency response will have a certain number of poles and zeros, and the number of poles and zeros will depend on the number of nodes that the signal passes through. The number of poles would depend on the number of nodes that the signal passes through. The number of zeros would depend on whether there is a phase shift through the different paths. Clearly, in this case, you do expect a phase shift, because if you look at the current through M1, for example, so maybe we can draw that on a different page. If you look at the current through M1, so the current through M1 passes through this node. So let us say that was node 1. Sorry, I don't want to name the nodes. So that passes through this node. So you will get a pole from that. It passes through this node. You will get a pole here. It passes through this node. It passes through this node, and finally at the output. So clearly, you expect I1 to pass through these 5 nodes. So you expect, and of course the output node. So you expect 6 poles in the expression for I1 over V out over I1. And if you look at I2 of course passes through this node and the output node. And as you can see, I2 only has 2 poles. And now these two currents get summed at the output. You can clearly see that there is a phase shift between the two paths. You do expect zeros in the transfer function, and now because there is such a large difference between the number of poles in the two paths, you expect several zeros in the transfer function. Now, two things. First of all, I would encourage you to think about the number of zeros and number of poles that you can get out of the circuit. If you so desire, for your own benefit, it might be useful to quickly do the small signal analysis, assuming a capacitance at every node. That will give you some insight. The analysis is expected to give you some insight as to the number of poles in each path. And when you add the two currents, you will also be able to see the formation of the zeros. And it will also give you insight as to the number of zeros that you would expect from this particular structure. Number 2, we also want to know what is the dominant pole in this particular structure, and as you might expect, you should expect that the largest capacitance comes from the load capacitance, because in some sense this is still a single stage op-amp. So this is still a single stage op-amp because this is the dominant pole. The output pole is the dominant pole. So you still expect this to be a single stage op-amp. And in other words, if you were to draw the equivalent circuit for this particular circuit, for this particular op-amp, it will look like an operational transconductance amplifier with a certain output impedance and a certain capacitance. So this is RO, and you have CL, and it has a certain transconductance. So if you were to look at the overall output, you are basically trying to create, you started from a one-stage op-amp which had a simple transconductor. You went to the telescopic op-amp which looked like a better transconductor. And now you have a folded cascode which still looks like a very good transconductor, much better than the regular original one-stage op-amp because R out is large. But the swing limits are expected to be better than that of a telescopic op-amp. So I would encourage you to, as an exercise, I want you to think about the swing limits of the folded cascode op-amp in unity gain feedback. So you need to convince yourself that the same problem that you had with the telescopic op-amp, where you had a swing limit limitation when you connected the op-amp in unity gain feedback, does not exist for this folded cascode op-amp. I will just remind you that from the basic structure, this is just a quick hint that the input common mode is now somewhat isolated from the output common mode in this particular structure. So you should apply the unity gain feedback on this particular structure and convince yourself that it really does not have the same problem. What about the coming back to the frequency response? So the in such a structure, you expect it to be a very good integrator. You expect the unity gain frequency to be dominated by the dominant pole, and clearly that should be GM1 over CL. Of course, the dominant pole omega D should be at 1 over R out CL. Because this particular op-amp has a much larger output resistance, it will have a much smaller dominant pole compared to a regular 5 transistor one stage op-amp, which we studied right at the beginning, even before the telescopic op-amp. So we are now in a position to also look at the input and output common mode ranges of the particular telescopic op-amp. So let us first look at the input common mode range. We will now assume that the input common mode is VCM. Let us say that I should apologize. I should add the bias voltages at these nodes because they are not left hanging. You have to have a bias voltage. I'll call them VB9 and VB5 and VB0. So there are 4 voltages that need to be applied to the folded cascode op-amp. VB0 for M0, VB9 for M9, VB3 for M3 and VB5 for M5. So for completeness sake, let me make sure that the voltages are added here also. So now we are in a position to study the input and output common mode ranges of the folded cascode op-amp. So let us now assume that the input common mode starts to drop. So let us say we decrease VCM. What is the common mode at node X, for example. So clearly the common mode at node X, so I'll call that Vx. Vx has to be Vb3 plus Vsg3. So the common mode at node X is fixed, relatively fixed, because Vb3 is fixed and the currents in the transistors are assumed to be fixed. Therefore, if you start decreasing VCM, all the other transistors are expected to remain in saturation till some transistor goes into triode or cutoff. Now, as you can see in this case, Vx stays constant, but VCM is decreasing. M1 moves away from triode, but it carries the same current. Therefore, what will happen? The drain node of M0, so I'll call that VT0, reduces and it follows VCM with a difference of VGS1. So when you try to reduce VCM, the input common mode voltage, VD0 reduces, which is the drain voltage of M0. So M0 clearly goes towards the triode region. So the minimum value of VCM is equal to VGS1 plus VD sat 0. So this is the minimum value. Beyond this, M0 goes into triode region. Now what happens if you start increasing VCM? This will give you the maximum limit. Clearly that will happen when M1 goes into triode, M1 or M2. That is because nodes X and Y are held constant at VB3 plus VSG3. Therefore, the gate voltage of M1 is increasing, the drain voltage is constant, so clearly it is moving towards triode region. And VCM max will be given when the transistor M1 or M2 goes hits the edge of triode region, and that can happen when the gate rises to one threshold voltage above the drain voltage. So the maximum voltage is Vx plus Vt1. Vx is clearly Vb3 plus Vsg3 plus Vt1. So the reminder, node X is at Vb3 plus Vsg3 and the gate voltage can rise one threshold voltage above that before M1 or M2 hits the edge of the triode region. So this is the maximum value of VCM. So therefore the input common mode range is this overall range of VCM min to VCM max. This is the input common mode range of this op-amp. What about the output common mode range? So now let us find out what are the maximum and minimum voltages that can be achieved at the output. The maximum voltage that can be achieved at the output, so VOCM, if the output voltage starts increasing, you can see that the gate of M4 is held constant, which is VB3, and the drain voltage can rise one threshold voltage above the gate, and for the PMOS transistor. So therefore VB3 plus VT4. This is the maximum voltage that the drain of the PMOS can achieve. VOCM min similarly is determined when the NMOS transistor M6 hits the edge of triode region. Gate of M6 is held constant at VB5, but the drain is swinging lower. It can swing 1 VT below the gate. So the minimum value is VB5 minus VT6. Now please note that VB3 and VB5 themselves and all the bias voltages are under the designer's control. So for example, VB5 can be as low as VDSat 8 plus VSG 6. So clearly these two are all these bias voltages are design parameters. For example, you could design a current mirror consisting of M5, M6, M7, M8 to be biased such that the output can go as low as 2 VDSat. So VB5, if VB5 were equal to VDSat 8 plus VGS 6, if this were the case, then you can see that VOCM minimum is now equal to VDSat 8 plus VDSat 6. So clearly VOCM min can be very low as long as the bias voltages are chosen appropriately. Similarly, VOCM max can be as high as VDD minus VDSat 10 minus VDSat 4. So let us just quickly write that down here. So if designed properly, I say can be low, but what this means is that you need to choose VB3 and VB5 etc. Carefully. I'll just simply write it as, since I'm writing it as sum of 2 VDSats, I can just write it as 2 VDSat. In other words, it is VDSat 8 plus VDSat 6. And similarly, VOCM max can be as low as VDD minus VDSat 10 minus VDSat 4. So the swing limits can be designed to be moderately high. This is still of course not as high as the regular 5 transistor one stage op amp that we initially studied, but it is definitely it can be designed to have certain moderate values. And now let us look at the other parameters of this op amp. We have looked at the input common mode range, we have looked at the output common mode range, and we have looked at the gain, and we have looked at the frequency response. So the other two parameters that we are interested in are the noise and offset of the folded cascode op amp.